Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome students. Starting with the name of Allah, who is most merciful and beneficent. In the previous lecture, we discussed about how to obtain the transfer function of an unknown system, and then we start our discussion on second order system. And in second order system we discuss its transient response. So we have seen that there are four types of transient responses for second order system, and we have discussed overdamped response in the last lecture. So in this lecture we continue our topic of second order system, and will discuss the underdamped response. I am writing the transfer function for underdamped response, s square plus 2 of s plus of 9, and this is the transfer function. This is our input r of s, and this is our output c of s. Here we change the value of a equals to 2 to get the complex roots. In overdamped system we take here 9, but in underdamped system we took here 2. So to get the complex root, if now I apply this unit step input here, so the output response will be and our input here is 1 over s, so we can write s square plus 2 of s plus of 9. And its roots will be s minus 1 plus of j under root 8 and minus 1 minus j under root of 8. So these are the roots, and it is clear that the roots are complex. So we know that if the roots are complex, then the response will be underdamped response. So the output response in time domain will be 1 minus e power minus t and cos of under root 8 of t plus under root 8 upon of 8 sine of under root 8t u of t. I directly write the output response in time domain because we have solved this type of equation which have complex root in chapter number 2. You can refer lecture number 4 for its solution. We can also write this output response equation as 1 minus 1.06 e की power minus t cos of under root 8t minus of 19.47 degrees u of t. Here also these brackets. So the question is how this equation is transformed into this equation. So for that I have used a trigonometric identity. You know this identity, cos alpha minus beta will be equal to cos alpha cos beta plus of sin alpha sin beta. So if I compare this term with only this part, then here cos alpha, not cos alpha but alpha, here alpha is equal to under root 8t and cos of beta will be equal to 1 and this is sin alpha term and this term under root 8 upon 8 is our sin beta term. So if we want the value of beta, so for that I am using tangent beta is equal to sin beta over cos beta, which is equal to under root 8 over 8, because the value of cos beta is 1. So if you want to get the value of beta, tangent inverse under root 8 over 8. So finally the value of beta will be 19.47 degree. So this is the angle. So if we want to calculate its amplitude, then the formula for amplitude will be cos beta square plus of sin beta square. So here I am putting the value of cos beta and sin beta. So value of cos beta is 1 and the value for sin beta is under root 8 over 8 square. So here the amplitude will be 1.06. So this is the angle which I have used over here, and this is the constant term which I used over here. So in this way I have transformed this equation into this equation. This function has a pole at origin that comes from the unit step input and two complex pole that comes from the system transfer function. We now compare the response of second order systems to the poles that generate it. So for that, first we will compare the pole location to the time function. So these are the pole location, and then we will compare the pole location to the plot. These are the pole location and these both are the plots. So from the figure, this figure, the pole that generates the transient response are, I can write here, S equals -1 and plus j under root of 8, and the second pole, the same pole with the negative sign. By comparing these values to the output response, these pole values with this output response, we see that the real part of the pole matches with the exponential decay frequency of the sinusoid amplitude. I am writing here the output response in time domain. So it is 1.06 e to the power minus t cos of under root 8t minus of 19.47. So this is the exponential decay frequency, which is here -1, and the real part of the pole is also -1, and the imaginary part of the pole matches the frequency of the sinusoidal oscillation. So this is the imaginary part, and it matches with the frequency of the sinusoidal oscillation, the frequency of cos function. Now we will compare the pole location to the plot. So this is the figure showing a general damped sinusoidal response for second order system. Here the transient response consists of an exponentially decaying amplitude generated by the real part of the system pole times a sinusoidal waveform generated by the imaginary part of the system pole. So this decaying frequency, this decaying part is basically produced due to this exponential function, and this oscillating part is basically produced because of this cos function. This sinusoidal frequency is given the name damped frequency of oscillation. Omega d. And when these oscillations are eliminated, the system approaches to the steady state value here. Steady state value, and this steady state value is generated by the input pole at origin. This example demonstrates that how knowledge of the relationship between the pole location and the transient response can lead rapidly to the response form without calculating the inverse Laplace transform. So now we consider the case of undamped system. So for undamped system, the transfer function will be this. This is our input and this is our output. So here we eliminate the value of a to get the imaginary roots. We know that if our roots are imaginary here, then we will get the undamped response. So if we apply here the unit step input, then our output response will be 9 over s squared plus of 9. If I factorize it, then the two factors are both imaginary. So these are the roots for this equation. Now the output response in time domain will be 1 minus cos of 3t. Again, I am writing the output response directly in the time domain because we have covered this type of question in chapter number 2, and you can refer chapter number 2 for its solution. So here in this function we have a pole at origin, this that comes out from the unit step input, and two imaginary poles that comes from the system pole, from the system transfer function. The input pole at origin generates the constant force response, this, and the two system poles on the imaginary axis generates a sinusoidal natural response, this, whose frequency is equal to the location of the imaginary poles. Its frequency means the frequency of the cos function is 3, and it is equal to the value of imaginary poles, which is also which is also 3. So the output response graph and pole plot for undamped systems are over here. This is the output response, and this is the pole plot. So here we observe that there is no real part in the pole pair, and due to this the value of power of exponential term is 0. So if I can write it as e की power 0t cos of 3t. So here the exponential frequency is 0, Therefore, the output response will be 1 minus cos of 3t. Since there is no exponential term, the oscillation produced due to this cos function will not eliminate as in case of underdamped response. Here you see that these oscillations are not eliminated. In underdamped response, we see that this negative exponential term is present in its output response, and we know that if the value of time increases, then after some time this whole term will become 0, and only this part of the output response will remain present. So you can see that here in underdamped response we have oscillations, but these oscillations are eliminated after some time because of this exponential term. And in undamped response we do not have any exponential term, so these oscillations will never die out. Now we consider the case of critically damped response, the last case. So 9 upon s square plus of 6s plus of 9. So this is the transfer function for critically damped response. Here we apply our input, and here we get the output. So here we put the value of a equal to 6 to get the real and repeated roots. So if we apply here the unit step input, then our output response will be 9 divided by s, and s square plus of 6s plus 9, and if we factorize it, then its factors will be s plus 3 whole square. So here we see that our roots are real and repeated. So the output response in time domain will be 1 minus 3t e to power minus 3t minus of e to power minus 3t. This function here has a pole at origin that comes from the unit step input, and two real and repeated poles that comes from the system transfer function. The input pole at origin generates the constant force response, this part, and the other two poles at the real axis generates the natural response. This whole part. This natural response part consists of an exponential and an exponential multiplied by time, where the exponential frequency is equal to the location of the pole. Here you can see that the value of exponential frequency is also 3, and the pole location is also 3. So we can see the output response and its pole plot here. So both the poles are located at the same location, which is -3, and this is its output response, that is look like the first order system. So we can say that the critically damped response is the fastest possible response without having the overshoot, and also this response is a boundary between the underdamped and overdamped response. It means that if we increase damping in the critical damped response, it will become an overdamped response, and if we decrease the damping, it will become an underdamped response. So now we can summarize our discussion. So in second order system, we see that we have 4 types of responses: overdamped, underdamped, undamped, and critically damped. In overdamped response, we have 2 poles that are real, but they have different values, as it is stated over here. And its natural response consists of 2 exponential terms, this one and this one, with the time constant equal to the reciprocal of the pole locations. It means that in first order system, we see that the response is written as for first order system. So here time constant is equal to 1 upon A. So by this statement, the reciprocal of pole location means that here the time constant for this and this term are respectively 1 over rho 1, and for the second term it will be 1 over rho 2. And in underdamped response, again we have 2 poles that are complex in nature, and its natural response consists of damped sinusoid with an exponential envelope whose time constant is equal to the reciprocal of the pole's real part. So this exponential term produce the envelope that we have seen here, this envelope, and its time constant is basically equal to the only real part, means the pole's real part. So its time constant will be 1 upon rho d, and the radiant frequency of the sinusoid Here we have cos term as an sinusoid. The damped frequency of oscillation, it is also known as the damped frequency of oscillation, is equal to the imaginary part of the poles. So its frequency here, which is also known as the damped frequency, is equal to the real imaginary part, which is written over here. And in undamped response, again we have two poles, but they both are imaginary in nature, and its natural response consists of undamped sinusoid with the radiant frequency equal to the imaginary part of the poles. So we can see over here the frequency of this sinusoid is equal to the imaginary part of pole. And in critically damped response, again we have two real poles, and both the poles have the same value, and its natural response consists of two terms, in which one term is an exponential whose time constant is equal to the reciprocal of the pole location. Here you can see here, this is its time constant 1 upon ρ1, and it is equal to the reciprocal of the pole location. Another term is the product of time t and an exponential with the time constant again equal to the reciprocal of the pole location. Here you can see here. So these are this diagram. Now this diagram shows the step responses for second order system damping cases. So here we see that the overdamped response is the slowest response, and then if we decrease the damping of the system, the response speed will increase, as you can see over here, decrease the damping. If we decrease damping, then our response time to reach the steady state will reduce, and critically damped system approaches to steady state value faster than overdamped. And if we further decrease the damping, then we got the underdamped response, and its response time, here you can see, is more faster. This is more faster than the critically and overdamped response. And finally, in the undamped system, the response speed is very fast. The response speed is very fast, but it will never attain the final steady state value. So in the next lecture, we will discuss an example on this topic, and then we will start our discussion on general second order systems. Thank you.